Let's start the new chapter, electromagnetic waves. So first of all, it is necessary to understand that it is the combination of two words. The first word is electromagnetic, and earlier we have studied about the electromagnetic field. But what was that? So it is the mixture of or the combination of two branches of physics. And the two branches are, the first one is electricity, and it is the basically dependent on the charge. And the second one is the magnetic branch, and it is basically or it is magnetic physics, in which the fundamental or we can say the basic element of magnetism is, and this magnetic physics, yes, there is another word, magnetism, and the fundamental element is a magnet. And if we go into the detail, then it is consisting of North Pole as well as the South Pole. Now, what is the necessary to study this kind of branches? We have earlier studied about their application, and from that application we conclude that it is the necessary thing to understand the combined effect of two branches, means electricity and magnetism. Now the other word comes is of waves. Now what are the waves? You might have studied 11th science semester 2. So the waves are nothing but an oscillatory nature. Means this kind of imaginary figure can be considered as wave. So from how many waves you are aware? Sound waves, whatever we are speaking, it converts into the form of a sound wave. We also familiar with radio waves and many other kinds of waves which are we have studied earlier, but it is not necessary that we should go into the detail at this time. But what should be the observations we have to make to understand the combined word electromagnetic waves? And for that I am giving you some analysis, and in my analysis I am giving you some questions. You would have seen the golden sun that is rising from the east, and it sets in west. But this is the first question. The second question is, you have observed colorful flowers on green plants trees. And you have also seen the colorful birds in the sky. So, With these two observation or these two particular question, how can we analyze such thing? So what is the actual reason that we can analyze such thing? So the basic reason is, or the basic fundamental element which is responsible for such analyzation is dependent upon electromagnetic waves. So if there does not exist electromagnetic wave, then we cannot analyze such kind of things. And our eyes can see the picture. This is most important. And that picture is in the form of electromagnetic wave. Now, the visible radiations which are produced from the sun and they are coming towards the earth. So these are the visible radiation which are coming towards the earth, and the animals, birds, fruits, flowers or any kind of things reflect electromagnetic waves in different wavelengths corresponding to their colors. So suppose here is the one particular fly in the sky, and that is reflecting these kinds of wavelengths according to their particular color. So each wavelength is consisting of a particular color, and that color is reflecting to our eyes due to the electromagnetic waves. And it is not necessary that each wavelength is of particular color, but it should be of a particular frequency, and that frequency is consisting of color. Now, who had given the contribution in the study of electromagnetic waves? So, in 19th century, Maxwell presented the laws of electricity and magnetism. And for your information only, he had actually given the four basic equations on which the branch electromagnetism or electromagnetic is totally dependent. And these laws were similar to the Gauss law, Ampere's law, and Faraday's law. And it is also related to the formation of closed loops in the magnetic field in the form of differential equation. So as I told you, Maxwell had given 4 equations, and that 4 equations are related to electric field and magnetic field respectively. Now, during the study of Maxwell's equation, and they are actually the differential equation, it was concluded that some terms are missing in the Ampere's law. So, this particular topic we are going to discuss just apart from this, but how they concluded that. So, Maxwell postulated that the missing term in the displacement current. So, the term which was missing is existing in the displacement current. Now, what is the displacement current? We will go through it and find out which term was actually missing there, and the resulting differential equation for the electric field and magnetic field were identical with the wave equation. So the differential equation after adding the missing terms are known as the wave equation. But from this wave equation, it was studied that the velocity of the wave is equal to the velocity of the light in vacuum. So this is one important result. And according to this fact, the light waves are nothing but the waves associated with electric field and magnetic field B. So, the light waves are also known as electromagnetic waves. And now, we will study about the missing term analysis. That means before that we have to consider this displacement current. So let's start the analysis to find out the missing term. Now the displacement current. We have studied the effect in Ampere's law, or we can say that was a falseness or a defect type in Ampere's law. Now Maxwell's term has a certain appeal in that missing term, and the answer was that there is a missing term in the case of displacement current. And here what they have done, Maxwell has changed the magnetic field induces electric field, and this is the Faraday's law. But if you look at the equation in the Ampere's law, then it is not satisfying this result. In that case, electric field induces the magnetic field. So it opposes the Faraday's law, but we have considered that the Faraday's law is universal and fundamental. So the result which was derived by Ampere was totally found to be wrong, and the real confirmation of Maxwell's theory came into 1887 by Hertz experiments on electromagnetic radiation. Now see, these radiations are totally different. So this results in Ampere law. The term which was missing in this equation, closed integration B dot dl is equal to mu 0 I, where I is the displacement current, plus something was missing about it, and that was according to Maxwell's opinion. And Maxwell called this term or this missing term as displacement current. And before now we move further, just recalling the Hertz experiment so we can get the actual idea about the displacement current. So this is actually the Hertz experiment, or we can say the simple arrangement. And here the word displacement current is not actually a kind of a current. But it is the motion of charges. It can be clearly demonstrated by considering a simple capacitor. You can see these are the plates of capacitor, and when voltage supply or power supply is connected, then what happens? See over here. This current I enters the positive plate and leaves the negative plate, which is parallel. See this parallel plate capacitor, because both are connected parallelly. So this kind of arrangement of capacitor is known as parallel plate capacitor, and these are also known as parallel plate capacitor. So both kind of arrangement you can take. Now this current will not continue for longer time. So after a particular time interval, the value of flowing of this current will be 0 after a particular time interval. And when it becomes, whenever the capacitor is fully charged, then the current will become 0. And in order to find out the value of current, you can connect a meter over here and you can measure the value of current. So it is very easy. But if the capacitor plates are put very close to each other, then what happens? Then the field between them, electric field E is equal to 1 over epsilon 0 sigma. Means E is equal to sigma upon epsilon 0. But what is this sigma? Current and charge density. So charge per unit area. And I am writing it this way. The total charge per total area. So sigma is equal to Q over A, where Q is the charge on the plate, means total charge, and A is area. Now, when the capacitor is getting charged, See, each and every word is important. When the capacitor is getting charged, means it is not fully charged yet. So at this time, I can differentiate this equation. So del E by del T, and this is what? The differential equation, what we are going to find out, is equal to 1 over epsilon 0 is constant, area remains constant. So it is del Q by del T. But it is for only one particular term, then I am writing over here dq by dt. And this dq by dt, rate of change of current, rate of change of charge, that is current. So it is 1 over epsilon 0a into I. Therefore, now I am making some kind of change in this equation, taking epsilon 0 on the left hand side. Therefore, epsilon 0 del E over del T is equal to 1 over A into I. And that is the current density. If you remember, current per unit area. And that is denoted by J. But here we are talking in terms of the displacement current, then I am putting the subscript D. And that's why I have written JT. Now, here if you see, if you want to find out the value of displacement current, then I have to make it object, and therefore my equation will look like epsilon 0 into A into delta E over delta T is equal to I, and that is called displacement current. Now in the form of integral, I can write down this equation. Epsilon 0 integration delta E. Now see, this current is flowing in the particular direction. This electric field also having particular direction, and hence I am writing all this quantity in a vector notation. So del E by del T into, now if you take this total area into integration, then I have to consider this small element of area, that is dA, and I can write down this I, or I can use the subscript D for displacement current. And if we add the integral form of displacement current in Ampere's law, means I want to determine the value of one kind of Maxwell's equation. So what was the Maxwell's equation? Ampere's equation. Closed integration D dot dl is equal to mu 0 I at that particular time, and that was correct value. So I am writing it as IT. And now I am adding this particular term with the coefficient mu 0. So that is mu 0 epsilon 0 integration del E by del T into dA. And so the equation will be closed integration B dot dl is equal to mu 0 IC, and the second term was mu 0 ID is equal to mu 0 into IC plus ID. And this is now the faithful relation for Ampere's law as well as Maxwell's law. But we are thankful to Hertz's experiment by which the opinion comes true. And this particular equation is known as Ampere-Maxwell law. And this equation suggests that the total current passing through any surface, total current means IC plus ID, passing through any surface of which this surface should be this kind of condition. The closed loop is the perimeter of the sum of the conduction current as well as the displacement current, and outside the capacitor plate. So this is about inside, and for outside of the capacitor plate or outside of the surface particularly, there is conduction current, and inside the capacitor there is a displacement current. So the figure which you have observed, in that case the current which was flowing inside the plates of capacitor, or we can say between the plates of capacitor, that is known as displacement current. But you cannot actually measure the value of this displacement current. And with this, our article number 3.1 is over. And now we will switch on to the two types of waves